Thank you, and good evening, Chester. This is the first of two short talks, as you've heard. This first talk will be about what the professionals are doing, and the second talk will be what one particular amateur is doing. So this is JWST+2. The +2 indicates that I'm talking about its second year of operation. And you might get the hint from the holly and ivy in the top left and bottom right corners that this was originally written as a Christmas talk because, of course, the James Webb Space Telescope was launched on Christmas Day. So 1 year after the launch, I decided to basically put together a talk which was a 1-year update. This is the second year update. So I'm sure you know a lot of the background, but just for the sake of a couple of minutes, let me just remind us all where we stand. So the James Webb was put together over many, many, many years and a lot of testing, and then it was folded up like a piece of origami and put on the top of a rocket and launched on Christmas Day 2021. It was a piece of origami mainly because the mirror is so large. Remember, the mirror is significantly larger than the mirror of the Hubble Space Telescope. There's the Hubble, 2.4 meters in diameter. There's the James Webb, 6.5 meters in diameter. So to get it on top of a rocket, it had to be folded up. So we have this segmented design which unfolds into a large mirror. The larger mirror means collecting more light, which is fantastic for looking at faint objects. In principle, it means higher resolution if you work at the same wavelength, but the resolution of a telescope depends on the size of the mirror relative to the wavelength of light that you're trying to image. And although the mirror is larger, the wavelengths are larger because the James Webb works in the infrared rather than the visible. So the actual resolution of the two telescopes is, roughly speaking, the same. Let's remind ourselves where it operates. There's the electromagnetic spectrum. There's the visible light compressed into that small area there, that small run. And the Hubble Space Telescope works mainly in the visible, but also a little bit in the ultraviolet, a little bit into the infrared. The Spitzer Space Telescope works out here at the very long infrared wavelengths, and the James Webb effectively plugs the gap in between the Hubble Space Telescope and the Spitzer Space Telescope. Launching on Christmas Day, they sent it away from the Earth and sent it out to a parking spot called L2. There are 5 parking places in Earth orbit that will allow it to go around with the sun, so it's effectively a parking place with respect to the Earth. It's still moving, but it's static with respect to the Earth. They don't actually want to place it at L2 because that would be in the Earth's shadow, so they actually put it in a small orbit around L2. So the James Webb and a few other spacecraft are now parked around L2. Gaia and other telescopes are going to be placed in the same position. And because the noon side of the Earth is facing the sun and the midnight side of the Earth, of course, is always on the opposite side of the Earth, basically you can think of the James Webb Space Telescope as basically sitting 1 million miles above midnight because it's always above the midnight point on Earth. So that's where it's currently sitting. It's got 2 main tasks. One of them is because it's working in the infrared, it's able to look at very dusty environments such as early star formation and early planet formation. And the other reason for moving from visible into infrared is that the very distant galaxies, remember the universe is expanding, and so the light from very distant galaxies is getting stretched from possibly the ultraviolet or the visible part of the spectrum. They're getting stretched into the infrared. So we would expect very distant galaxies to look brighter in the infrared than perhaps they do in the visible part of the spectrum. So one of the jobs of the James Webb Space Telescope is to look back in time at the most distant galaxies with a finite speed of light. The more distant galaxies, of course, means that the light left them a long time ago, and hence we're looking back in time. This is a timeline at the top here, the Big Bang on the left, and that's us here 13.8 billion years later. And the question is, how far back in time can we actually look with either the Hubble Space Telescope or the James Webb Space Telescope? Remember, as I said before, the universe is expanding, so the further back in time we look, the more light has been stretched, and we quantify this with the so-called redshift. How much the light has been stretched compared to its original wavelength. If you take a given wavelength and stretch it to twice that value, that corresponds to stretching it by an equal amount to the original wavelength. That means a redshift of 1. So a redshift of 1 corresponds to galaxies that are quite a few billion light years away. But we want to go back in time further than that. Ideally, we want to look back at the first billion years after the Big Bang. Why is that so important? Because that's when we think the first stars and the first galaxies were born. In that first billion or possibly even half billion years, that's when we think all of the action took place. After the Big Bang, after the cosmic microwave background was created, only a fraction of a million years after the Big Bang, there were the so-called dark ages, and we don't understand exactly how the first stars and the first galaxies came to be. If we expand that little section there and just spread it out so we can see it a little better, if we spread it out so we can see the first half billion years or so, the question is, how far back in time can we go? There's the redshifts. We're now not talking about a redshift of 1 or a few. We're now talking about a redshift of 10 or more. And so far, the Hubble Space Telescope has been able to see distant galaxies back to about that position. In other words, back to maybe 500 or 600 million years after the Big Bang, up to a redshift of about 10. The James Webb Space Telescope, as we'll see shortly, has got to roughly the same position, but it's hoped that the James Webb Space Telescope will be able to see fainter galaxies, more distant galaxies, hence further back in time, and be able to push that much further back towards the Big Bang, so that we hopefully will find the place, the time, when the first stars and the first galaxies were born. It is hoped that eventually, not yet, but after perhaps a few years of operation, the James Webb Space Telescope might be able to get us from where we are now at about 500 million years, hopefully push back to the very earliest times, perhaps 200 million years after the Big Bang. So that's one of the functions of the James Webb Space Telescope, is to look back in time and see how far back it can see. But in this short talk, I'm simply going to give a recap of what it's been doing in 2023. Once it got to L2 and was commissioned and calibrated and they checked all the instruments were okay, you perhaps remember the news release of these are the first images that came out of the James Webb. I'm going to leap right ahead another year because I'm now saying, right, that was 2022, what's been happening relatively recently? In other words, what's been happening in the last year or so, in 2023. And rather arbitrarily, I've just picked 12 things that I think are quite interesting. Not necessarily the 12 prettiest images, that's not what it's all about, but 12 scientifically relevant points. And I'm going to go through them almost 1 month at a time. So let's start with January 2023. This image was released, or a pair of images was released. It may not look very spectacular. What we're actually looking at is the dusty environment of a planetary system seen edge on. The star itself is where that 5-pointed star is. That star has been removed because when you're looking for planetary systems, the star dominates the brightness. So artificially, you have to take the starlight out before you have a chance of seeing what's left. In this case, the rather dusty environment of this planetary system that is forming. For those of you who've seen this on Earth, zodiacal light is the light in the plane of our Earth's orbit, the ecliptic, where there's a lot of dust, and occasionally you might see the zodiacal light after sunset or before sunrise. Anybody here seen the zodiacal light from England? You need nice dark skies, which is perhaps why you don't tend to see it from England. I've only ever seen it from Africa, where the skies are fantastic, and then before sunrise, I saw this cone of light coming up from the horizon. I wasn't sure what it was, and then I realized it was the ecliptic, and so we were seeing dust reflected in the plane of the ecliptic from the sun that hadn't yet risen. So in a sense, we're seeing the same thing. The zodiacal light is quite faint and rather tricky to see in our own solar system. So the fact that the James Webb Space Telescope has been able to see effectively the same thing in an exoplanet system is testament to the sensitivity that it can see the dusty environment similar to the zodiacal light seen in our solar system, but round an entirely different stellar system. So that's, again, a very good indication of the sensitivity and what we can expect for discoveries in the future. No, this is not an image from James Webb. This is an artist's impression, because back in February 2023, it announced that they'd found an asteroid. Nothing particularly amazing about that. It's a relatively small asteroid. It's only about 100 meters or so across. Now, we see lots of those anyway, but generally speaking, if an asteroid is only 100 meters across rather than a kilometer or 10 kilometers or anything much larger, we tend to only see those when they're relatively close to the Earth. This asteroid, 100 meters in diameter, was seen by the James Webb even though it is still in the asteroid belt. Nowhere near Earth. This is still 100 million kilometers away, but James Webb managed to pick it up. That's the good news. It is very sensitive to small asteroids. The bad news is it's not looking for them. This was picked up by accident. They were looking for something else. Somebody noticed in the same field of view, what's that tiny dot there? It turned out to be this tiny asteroid in the asteroid belt. So the James Webb is capable of picking up asteroids, even small asteroids, a long way before they are potentially hazardous and coming anywhere near the Earth. But as I say, the James Webb Space Telescope is far too valuable, and it's not going to spend its time looking for these asteroids. We're going to have to look for them with other telescopes on Earth. This is a Wolf-Rayet star now in March 2023. A Wolf-Rayet star appears to be an unstable star coming to the end of its life that's been sloughing off a lot of the outer layers. This particular Wolf-Rayet star, we think perhaps these sorts of stars are precursors to supernova. They tend to be massive stars. They are definitely unstable. This one, you can see this sort of knotty structure in the nebula around the star. It's thought that this particular star has been losing mass into the interstellar medium for probably thousands, if not tens of thousands of years. And originally it's been calculated that this star might have had a mass of about 30 stellar masses. It's been calculated that it's probably lost 10 stellar masses, 10 solar masses. In other words, solar mass just being the mass of our sun. Nothing particular about the mass of our sun, it's just a convenient unit to use. So this star has already lost 10 solar masses and it's got 20 solar masses left. Maybe this is going to go supernova before too long. So studying Wolf-Rayet stars is a good way of getting perhaps a supernova before it decides to go off. In April 2023, it took a picture of the planet Uranus, and we get the beautiful rings. Remember, Uranus was visited by Voyager 2 back in 1986, it was, that it went past. So, of course, Voyager had a much closer view of the planet Uranus, but it saw essentially nothing. There was no interesting surface detail as Voyager spent a few hours zooming past on its way towards its next rendezvous at Neptune. So in that sense, it was a little disappointing. Now we look back at the planet at our leisure in the sense that we no longer have a very tiny window in which to see the planet as the spacecraft passes it. We can now go and watch this planet at any time we wish. And in this particular case, the James Webb has caught the fact that there's now a very big cap at the pole, a very large polar cap, that seems to only show itself when the pole is actually pointing towards the sun. Remember, the planet Uranus has got a very odd tilt, unlike the Earth where the axis is pointing almost out of the ecliptic. This one is pointing almost in the ecliptic. So we've got a very big polar cap, and it also looks like the very bright spot on the left limb of the planet there appears to be a storm system. So perhaps Voyager in 1986 was simply unlucky and it happened to go past the planet when there was nothing interesting happening. But there is interesting things happening now. So every once in a while, James Webb is going to point back to the planet Uranus and other planets to see what's going on. Not only do we get a beautiful image of the ring system, we can start to watch the weather systems on this planet, an opportunity we didn't have with the Voyager spacecraft. In May, this was astronomy picture of the day. In May 2023, the James Webb Space Telescope has revisited a number of the systems that originally were looked at by the Hubble Space Telescope. This is Fomalhaut. This is the brightest star in the constellation of Pisces Australis, the southern fish. And again, this is an exoplanet system, and the very, very bright star in the middle has been blanked out by this black circle because otherwise it would just dominate the image. And we see some dusty rings, and the James Webb Space Telescope, because it's working in the infrared, is able to see structure in this planetary system that's forming that otherwise would be essentially invisible. Now, it's not quite on the same scale as our solar system. It looks like this system is somewhat larger, but we can get the hint of we don't necessarily see individual planets in this planetary system. Seeing exoplanets is always going to be difficult, but we do get the impression that there must be planets in this system because we can see rings that indicate that planets are keeping certain areas of this protoplanetary system swept clear. And as an analog, we might say, well, in a sense, this outer ring is a bit like our Kuiper belt, full of dust and icy bodies at a great distance from the sun, and maybe this inner ring is a little bit like our asteroid belt. The distances don't quite match up, but just as an analog, in effect, we're looking at a solar system in which we can see something akin to the Kuiper belt and something akin to the asteroid belt. Doesn't rule out the existence of individual planets. When we zoom into some areas, it looks like, is that actually a planet there in this rather dusty environment? Well, that's the image at one wavelength. The image at another wavelength seems to indicate, maybe not. Maybe this is just a little cloud of dust that happens to be a little more concentrated. It doesn't look to be dense enough to be an actual planet as such. So James Webb is going to keep an eye on these sorts of systems to see how much it can learn about early planetary formation. This is the Pandora cluster. This was, again, astronomy picture of the day, this time in June 2023. This was a cluster that had previously been imaged by Hubble. This is no surprise. Hubble has imaged an awful lot of things in its 30-plus years of operation, so it's no surprise to find that James Webb has gone back and revisited some of these. So we've got a lot of foreground galaxies, the large, bright areas, and this cluster, being very massive, is also lensing, through gravitational lensing, is lensing a lot of more distant galaxies as well. So some of these galaxies that are on show here are very distant. This particular image is a mosaic. It was about 4 images, each of which was exposed for 4, 5, 6 hours each, so it's a very deep exposure. You can perhaps tell it's a mosaic if you look very carefully, because the standard 6 diffraction spikes of James Webb occasionally get split, indicating that it's actually multiple images partially overlapping with each other. But it's a very deep image, partially imaged by Hubble, but now imaged more deeply by James Webb. And this single image, this single mosaic, actually provides a huge amount of information for anybody that wants to analyze it, because of the very distant galaxies that are appearing much like the Hubble Deep Field in years gone by. It's been estimated, I think they probably counted them by now, it's been estimated that this image that you're looking at has got something like 50,000 galaxies in it. And therefore, all of those galaxies are giving us information about what's going on close to us and what's going on in the distance, because we're looking at various distance scales here. So the more clusters that James Webb images and takes spectra of, the more information we get about galaxy formation close to home and galaxy formation in the distant universe. To celebrate 1 year of science operations in July of 2023, given that the initial press releases, remember, were in the summer of 2022, after 1 year of successful operation, they announced this is our 1-year anniversary picture. Hubble tended to produce anniversary pictures, not surprisingly, every year, and I guess James Webb is going to do the same. They chose the Rho-Ophiuchi cloud complex. This is a very complex cloud where an awful lot is going on. This is one of the closest star formation regions to us. It's only 400 light years away, which on a galactic scale is right next door to us. 400 light years is essentially nothing. Remember, the Milky Way is 100,000 light years across. So this is on our doorstep, and the red indicates there's an awful lot of hydrogen jets coming out of some early star formation here. We also have a huge cloud at the bottom, a nebula at the bottom, that looks like it's being excavated by the very strong radiation from that star right at the center. I thought this was quite interesting because Rho-Ophiuchi is a common astrophotographer's target for amateurs, and I thought, well, that's interesting. But I had a go at imaging Rho-Ophiuchi a long time ago, and I don't recognize anything in that image. It doesn't look like anything I remember. So I thought, I wonder if I can figure out where this was actually taken. Which bit of the Rho-Ophiuchi cloud complex is this? So I went back and checked with an image I took some years ago. It's a very pretty image with yellows and blues, which is why amateurs tend to go for it. That's the star Antares, the brightest star in the constellation of Scorpio. That's M4, a globular cluster. And there's Rho Ophiuchi itself in the blue there, a little triple star. And I wondered, where was the James Webb? And it took me a long time to figure out where the James Webb had actually imaged. And I took the top part of the Rho Ophiuchi cloud complex and thought it was in there somewhere, so I blew that up, and I thought it's in there somewhere, but no, I'm going to have to take a little bit of that and blow it up again. And eventually I realized that little smudge there, 1 pixel in my image, was effectively the entire James Webb image. That 1 pixel was the James Webb image. So no surprise that I couldn't recognize what it had imaged. And after I realized that, I then had a duh, of course moment on remembering that the focal lengths are rather different. The focal length I used to take that image on the left-hand side, a 135 millimeter lens, a standard little telephoto lens. What's the focal length of the James Webb Space Telescope? 135 meters, not 135 millimeters. So it's 1,000 times the magnification. So no surprise in going from my image to the James Webb image, 1 pixel of my image was effectively the megapixel image taken by the James Webb. And of course, they always have that dilemma. They can't possibly image large objects that cover a large chunk of sky. They've got to decide which particular piece am I going to image. They haven't got time to mosaic large images. The James Webb in August revisited supernova 1987A, the supernova that went off 40 or so years ago, a little less than 40 years ago, in the Large Magellanic Cloud. All the material we can see here is not material that's been thrown off by the supernova. Remember the Wolf-Rayet star we looked at just a few moments ago? This supernova probably might have been something like a Wolf-Rayet star earlier, and for thousands of years it's been shedding an awful lot of material. So way before it actually went supernova in 1987, it might have spent hundreds or possibly thousands or possibly tens of thousands of years shedding an awful lot of its outer atmosphere into the interstellar medium. And then it went supernova, and what we're actually seeing here is the shock wave from the supernova catching up with all the material that was thrown off thousands of years earlier. The shock wave will be moving through this material at a fair fraction of the speed of light, and this sort of ring of pearls effect we get here is the shock wave hitting the material that was blown off years and years and years earlier. And as time goes by, we'll see, if James Webb continues to visit this year after year after year, we'll see that shock wave getting larger and larger and larger as it travels out from the original supernova. So by watching the shock waves, we get more information about supernova, we get more information about what's in the interstellar medium, we get more information about the sort of material that's shrugged off before a star goes supernova. In September, again, another astronomy picture of the day. Here is a star, a very young star. Remember, our sun is a few billion years old. This star might only be thousands or perhaps tens of thousands of years old. Very much a newborn baby. The star is right in the middle, and we can't see it because there's so much dust in early star formation. Not even the James Webb looking in the infrared can see the star itself. So there's a star right in the middle, and there are clearly jets coming off in 2 directions, and those jets are slamming into the interstellar medium, producing shock waves. So we can see these rather dramatic shock waves coming off here. This star system is about 1,000 or so light years away, and again, it's close enough to give us a lot of detail to tell us how stars originally form. This one is quite interesting for a number of different reasons, partly because it's so close we can see a lot of detail in the jets as well as the shock waves that the jets produce. Why do we get jets in the first place? That's still an active area of research to understand how a collapsing cloud of hydrogen can give rise to a pair of jets coming off in opposite directions. But what has proved to be quite interesting for this system is the jets themselves look like they're almost braided, implying that maybe this is a binary star being born. Maybe what we're witnessing here is the birth of a binary star. So again, that will be watched with interest for the next few years and next few decades to see if we can actually see these jets changing year on year on year to give us more information about star formation. October 2023, this was one of the brightest gamma ray bursts ever seen. Not this thing on the bottom right, that's the galaxy which produced a couple of neutron stars which, when they were born, when they were made, they were kicked out of the galaxy. This sometimes happens depending on how the system is reacting to the supernova that produced the neutron stars or the two neutron stars themselves, because of the interplay of trying to maintain a constant energy, a constant angular momentum in these stellar systems. It's possible that when stars are born, they get kicked out. And it's thought that two neutron stars actually collided here. Even though they were born in this galaxy, they've spent the last few million years traveling at some speed away from the galaxy, and the two stars were in collision and produced a gamma ray burst and a gravitational wave. So in other words, two neutron stars going around each other very fast before they collide, just like two black holes colliding, produces gravitational waves and a burst of gamma rays. You don't get gamma rays when black holes collide because nothing escapes from the black hole. But with neutron stars, that's a little different. So this was called a kilonova to indicate that it was much brighter than you'd normally expect for a nova, a new star, but less spectacular than a supernova. But what's really interesting about this is not the tiny red dot there, which is what James Webb actually saw. It's the fact that it took a spectrum of what's going on around that kilonova. And it found an element called tellurium. Tellurium is element number 52. It's twice as heavy as iron. Remember, all of the elements up to iron can be born inside stars. Stars convert hydrogen into helium, helium into carbon, nitrogen, oxygen, all of the elements up to iron. But you can't make iron inside a star. You have to kill a star and either produce a supernova or collide neutron stars together. This is the first proof, if you like, that colliding neutron stars produce enough energy to make elements much heavier than iron. It was previously thought to be possible. A little while ago, it was thought that maybe only supernova can generate the really heavy elements. Now we know for certain that it doesn't take a supernova. Colliding neutron stars can produce heavy elements much heavier than iron. So that discovery of the element tellurium in this system was very significant. October 2023, the James Webb again revisited an old friend, the Crab Nebula. And in this particular case, we're seeing a rather milky environment here, which is an indication that we've got a lot of emission. Electrons are very energetic and moving in the magnetic field of the pulsar that's right in the middle. Where is the pulsar? Somewhere in there. I don't think we can see it in this image. But these wispy areas that seem to indicate a bit like in the solar corona, we sometimes see elements of the magnetic field of the sun. The same is going on here. We're seeing electrons accelerated to very high energies, and they are bending in the magnetic field of the inside of the pulsar that's inside the Crab Nebula. This was interesting for a number of different reasons, not only in its own right. They're trying to work out how much iron, how much nickel is in here to get an idea of if this is a supernova remnant, can we get an idea of how the supernova went off in the first place. But what is particularly interesting is the fact that we've got the equivalent image taken by the Hubble Space Telescope 20 years earlier. And if I can get this right and flick back and forth between the James Webb and the Hubble, and then back to the James Webb and back to the Hubble, if you pick one particular feature, perhaps one that's close to the edge of the screen here, then perhaps you can see that the James Webb image is just ever so slightly larger than the Hubble Space Picture image. It's been calibrated very carefully so that all stars are in the same place. But the nebula is quite definitely bigger in the James Webb picture because it was taken 20 years later. This supernova went off, according to our calendar, about 1,000 years ago. So a 20-year difference is roughly a 2% change in the size of the nebula, which is roughly speaking what we see. The nebula is 2% larger in all dimensions because it's 20 years older. So this confirms the fact that this supernova went off about 1,000 years ago. So it's interesting that it's taken it in its own right, and we're getting information about the physics of what's going on, but it's also nice that we have this time lapse between Hubble 20 years ago and James Webb now. The last image, astronomy picture of the day from November 2023, and this again is the James Webb looking back in time as far as it can go. We're back to the same galaxy cluster we saw before, Pandora's cluster, but now we're looking at a galaxy that's been lensed, so this is very much more distant than the galaxies that we see in the foreground. It's been calculated that we're looking at a galaxy that is an awful long way away. This galaxy, it's been calculated from James Webb by looking at the spectrum and working out how much the light has been stretched. We're talking about a redshift of 10. In other words, the wavelength of the light arriving on Earth is 11 times longer than it was to start with. It's been stretched 10 times more than the original wavelength. And that means that we're looking back to the first 500 million or so years after the Big Bang. Now, Hubble just sees it as a tiny dot, but rather importantly, when you look at it with an X-ray telescope, Chandra, we see quite a bright patch in the same area, in the same location. So, James Webb says the galaxy there with a redshift of 10, so this corresponds to 500 million years after the Big Bang, and an X-ray telescope says there's so much energy coming out of this, there must be a black hole there. So taking these two measurements in combination, that means black holes, really big black holes, existed only 500 million years after the Big Bang. How did they get so big so quick? Some people say, well, if you make stars and the stars go supernova, then you get a black hole, and eventually black holes merge with each other, and eventually you can build up to really big black holes. But no one can figure out how you can get that quickly in 500 million years. 500 million years for most people is not long enough for lots of black holes to merge together to make something that big and that bright. So we're having to change the way we think about the early universe. Maybe these weren't the result of stars dying and then becoming black holes and then merging together. Maybe really big black holes were made in one go, rather than lots of small stars putting together, building up into a supermassive black hole. So seeing a black hole that bright so early in the universe tells us that we have to have a serious rethink as to how we think the early stars and early galaxies were put together. So I've had my half-hour recap of what the James Webb has been doing for the last year or so. I normally give, as I've said already, this holly and ivy in the corner tells you that this is normally a Christmas talk, simply because of the anniversary of the launch. So at this point, I would normally wish the audience a very Merry Christmas. But given that we've just been through the spring equinox, I think I'll go straight over that and say thank you for listening.